You are now well on your way to becoming an expert coder and elite computer hacker. This past week in Foundations of Algorithms, we learned about control structures, if, else if, and else, along with switch statements. We covered order of operations and a whole bunch of different operators, along with all their traps and tricks. We also covered loops, for loops, and while loops, with a brief mention of do-while loops. We're setting ourselves up for an exciting next week. Functions, pointers, and arrays are on the table, and pretty soon, control of the entire world will be at your fingertips. I hope you're looking forward to the next week of Foundations of Algorithms.
Good afternoon, everyone. I've actually been missing you, even though it's only been a couple of days, so I'm glad we are back in this room again together. So as I promised last week, we're now starting off our weeks with a different historical figure from the history of computer science. This is Katherine Johnson. She was one of NASA's pioneers, and in fact, one of the early female computers. Computer was a term not just reserved for digital computers, for the actual machines. For a long time, it was reserved for the people who did calculations, who did complex calculations. And in her case, the kinds of calculations actually necessary to get rockets out into orbit. She, in fact, did the calculations for many of the first US manned missions. She spent 30 years at NASA and was in an office of what they called colored computers, then a term for the group of black women who were largely involved in doing these calculations. And then she later actually went on to work on digital computers too, calculating the trajectory for the Apollo 11 mission. She actually died only in 2020 and is celebrated as one of the women pioneers in computing. So that takes us now back a little bit to the kinds of computations that we're trying to do in our class and trying to get a handle on what we saw last week, which was this challenge we had that when we tried to swap things, we ended up swapping them only inside a function, and the result ended up not being passed back to the main function or back to the rest of the program. This happened because C was passed by value. This meant whenever we gave variables to a function, it actually made a figurative photocopy of those variables, and so any changes made to those variables did not impact the original copies. C functions operate on copies of their inputs and not the actual inputs themselves. So we have to come up with some kind of clever way of leveraging this fact while still getting the result we want, which is ultimately, in some instances, being able to change things from inside a subroutine, even when we want the changes to be reflected in the main routine. We want the changes from the caller, to be reflected in the context of the callee. The main function should see the changes, in some instances, changed by the functions that the main function calls. So this is just like photocopying a notebook with all of your notes and then making changes to the photocopy. It is not going to change the values in your original notebook. All you've done is written on that piece of paper. So when you modify the input to a function, after you return, unless you use what we call a pointer, nothing is going to have changed in the outside. So this is where we're going to start talking about this notion of a pointer, a variable that allows us to access somewhere else in memory and thereby start to pass these changes along through different parts of our program. So let's go back to our model of computer's memory. So at its very, very basic, it's just we can think of it as a series of boxes. We talked about how this maps to locations in the physical world, but this is ultimately what we want to deal with as programmers. Now, one way to do it might be to label it starting at 0 and going up normal counting, but we also discussed that instead what we're going to do is we're largely going to represent it as in hexadecimal in base 16 to allow us to write more addresses. Then we discussed a little bit about how the operating system is going to control where we're allowed to write and where we're not allowed to write to protect programs from each other. So that's mostly where we left off last week with a short discussion about how the operating system gives us an error message called a seg fault when we write to a part of memory that we're not allowed. One other point that we touched on briefly was talking about memory segments, which was how the operating system kind of sets up this separation between different areas of memory. All the variables that we've used so far, pretty much all of them with the exception of global variables and static variables that we'll come back to, are stored in this area of memory called the stack. And if we label our memory going from the highest address, so the very end of our memory back to the beginning, which is what this diagram shows, so the beginning of our memory is at the bottom, the end of our memory is at the top, the stack actually starts fairly close to the top, and then as you add things to it, you're actually going to lower and lower and lower memory addresses. So it's going backwards, it's going top down, which is kind of funny because we're building an upside down stack in this case, which with gravities involved doesn't work too well. Then we have a new segment, which we're going to talk about very briefly, which is called the text segment. And what this is where the actual code that you've written, the programming instructions for the computer are stored. When you think about it, when you write a program, the computer has to load that program somehow and then read each instruction one at a time. So where is it reading those instructions for? Well, when you type in your command ./hello to run your hello program, the computer copies whatever is in the hello file into this text segment, and then every time it needs the next instruction, it goes one address higher in the text segment to figure out what's the next thing that I should do. If the next thing that it is needed to do is create a variable, it goes over to the stack and puts another variable inside the stack. So we've got this nice separation between different parts of our program. We'll talk more about the other segments of memory later in the semester. So this gives us a hint about what seg fault actually means. It stands for segmentation fault. Because our memory is divided up into segments, a seg fault is essentially when we're accessing memory from a segment that is not permissible. So either the segment is protected or it's a segment that doesn't belong to us. Okay, so that covers our intro material for starting to learn about pointers. So we're going back to our little memory model. And along with the virtual memory model that I want to put up there, or the digital memory model, we also have a physical memory model that we are going to be using for today. And so I'm going to need some volunteers for today. I'm going to need a whole bunch. Have you ever seen one of these before, like an American-style mailbox? They're kind of cute. Okay, hold that up. And Finn, and what's your name?
Miles.
Miles, lovely to meet you. I do, so now you're going to be a permanent victim. So you get the lovely number 8 and pick one of our two friends over here. And you're going to have the number 7. Okay. And you're going to stand behind and hold the number over their heads. So you guys are nice and tall. And it doesn't have to, yeah, if you get tired of holding your arm there, because we're going to be here for a while, that's okay. And now I need one more volunteer who's going to help me with opening the boxes. Jiayi, your friend was Madeline. And yep. So can we have our lovely number holders hold up your numbers? Now, these are mailboxes, and we've got two different locations inside our computer. We've got location number 7 and location number 8. Now, Madeline, what I'm going to want you to do is tell me what is at these locations. So given that we are now storing stuff in here, I'm going to put these little flags up. The operating system is telling us that there are actually variables inside here. So Madeline, you're going to have to hold this microphone up. Say, test 1, 2, 3, I am awesome.
Test 1, 2, 3.
I am awesome? Great. Okay, you know how to use a microphone. So let's check what's inside mailbox number 8. Can you do that for me?
How do you open this? Oh, okay.
Or you can poke out your head if you want to wave to everyone. Can't be seen very well.
The number 7.
Okay, the number 7. Okay, let's close that one. And what's in this mailbox here?
The number 6 or 9.
Okay, so hold it up for everyone. What does it look like, a 6 or a 9? We'll let the audience decide. Hands up if it's a 6, hands on head if it's a 9. I think the 9s win. It is now a number 9. Okay, so say that it's number 9, okay. So number holders, I need to see those numbers above heads. They're going to have to work. Okay, so now what I want you to do is let's open one of the mailboxes and actually go to the location. You're going to get instructions from inside the mailbox, and we're going to follow those instructions. Okay, so let's open up this mailbox. And what does the instruction say? Okay, so you're going to follow the instruction?
Go to mailbox 7.
Go to mailbox 7, okay.
9.
And this is essentially what a pointer is. We have just discovered for ourselves what a pointer is. So it's just like a normal variable. These numbers could have been just like the number 9. Doesn't matter if the number 9 refers to a place or an age or a time. It could be 9 a.m. But Madeline was very intelligent. She knows that addresses are just numbers too. And so what we could do is we could open a mailbox, look at the number inside, and go to that location. Now, this is going to get confusing fast, so we're going to need some clever ways of dealing with it. Now, you guys hang there for a minute. We'll get back to you soon. And so what we've essentially done here is represented our computer's memory using our physical analogy here. So instead of having 2 mailboxes, you can think of a computer as having a very large number of these, each with their own street address. Now, one other thing you'll note is that my addresses here are not going up from, firstly, they don't start at 0. Why don't they start at 0? 0 is reserved for null, so that's a special address to tell us that this is not a valid pointer. That's a good thing for us to do. And the other interesting thing is that they go up in like what looks like 8, but I've got this 0x here, which if you remember from last lecture was the way we say that something's in hexadecimal format. But can anyone tell me why we're going up 8 at a time? Why are we going up 8 at a time? And it was Pranav. Okay, let's borrow that for a second. Okay, can you catch? Oop, that was a bad throw. You can catch, I can't throw.
Because there are 8 bytes.
Yeah, so there are 8 bits, and what we want to do is it'd be a little complicated for us to design circuitry that is going up bit by bit by bit at a time and having one address for every bit and having our circuitry work efficiently with that. So we were asking, Pranav was telling us that the reason we're going up 8 at a time is because there are 8 bits in a byte, and a byte is kind of the smallest addressable unit that we're going to use. This is the smallest unit that we're going to run our calculations on, and this was just for a reason of optimizing our circuitry and somewhat of a historical accident. So we could have made it 16, we could have made it 32. It's nice to do it in powers of 2 because that works well with the rest of our design, but there's nothing special. However, when you want to access a computer's address, you're always going to access it in these increments of 8 bits, or 1 byte at a time. And so what we have here is we know that each character only takes up 8 bits. After all, it goes from 0 to 255. So we can store that in one set of 8 bits, and here we have the word hello. Now you'll notice that I've put a /0 at the end. A /0 is just a fancy character that we can use to actually represent the number 0, the character that the character that has the ASCII value 0. And we're just going to use that as a marker to say, okay, that is the end of our set of letters. We'll talk more about that when we get to strings soon. So 1 byte is 8 bits. So the next address is always going to be +8, but because we're counting in base 16, that's going to give us this funny pattern here, which instead of going from 8 to 16, we're going from 0x8 to 0x10. That's counting another 8 in base 16. So the other way we could represent this is instead of having the letters HELLO, you guys are already smart, you've been in my class a little while now, so you know that each letter has a numerical value according to their ASCII code. So let's just display that instead. So now we have those numbers up there in our boxes. So 104, 101, 108, 108, 111, and then our null byte, our /0 at the end, is represented by a 0 over here. But this is still not looking quite the same as either our segment demo or our mailbox demo. So let's take this a little bit further, and let's just put it vertically. So now we have an upside down version of the computer's memory. I'm going from the lowest address to the highest. It doesn't matter which way you turn it. The computer's memory still contains the same things, whether you're holding your laptop this way or whether you're holding your laptop that way. And so what we can do is just what Madeline was doing for us before. She was opening the mailbox, and let's do this one more time.
7.
Oh, we've lost the... Pranav's still got it. Okay, Pranav, do you want to get it back to us? I like this game. Figure out the most efficient path for the microphone. There we go. So we've got the number 7, and what we're going to do, Madeline, we are going to just read it off the slide. Okay, we have room mics back. Wonderful, thank you. Okay, going to pause that for the minute, and then we'll do a mic swap in a little bit. Okay, so Madeline, what are we going to do with what's inside the mailbox?
Go to the address.
We're going to go to the address, so that means we're interpreting the number inside the mailbox as an address. So we could interpret it as a character, we could interpret it as an integer, we saw that we could interpret things inside different variable locations as decimal numbers, but now we're going to interpret it as an address. Okay. The only thing is we've probably got some questions about how we do this. So how do we know which variable is a number and which is actually an address? Madeline, tell us how you realized that that was actually an address.
Because there's a variable with the same name.
Okay, not quite. How did you do it? What was your thought process? Like, explain to me, like, you opened the box and you saw a number there. How did you figure out that that was actually an address?
Because the next memory, there's an address for 7 also.
Yeah, probably because we structured this little demo such that it was really, really obvious to you guys. But our compiler has a bit more of a problem. It can't do this automatically. It's not quite that smart. I'm going to steal this from you, and we will ask Rachel, right? No? Jessie, sorry. That's why you didn't look up. Okay, Jessie, so what do you think, let me phrase that again. Jessie, what do you think we can do to tell the compiler how a variable should be treated?
Maybe using like keywords like static.
You're on the right track, so how do we already let the compiler know how to treat a variable?
Like you write it in the code.
Yeah, well, what do we write? Let's say I make a new variable. What's the 2 pieces of information I give the compiler?
So like the data type and the variable name and the value.
Yeah, so which of those things do you think is a good place to tell the compiler or to tell the computer how we should treat it in terms of whether it's an address or whether it is a letter or
maybe from the data type?
from the data type? That's great. So essentially what we want to do is we want to have some special kind of data type that's going to signify to the compiler that the particular variable, it is just a number. After all, everything's just a number on the computer. But that this particular number, we're going to use it like an address. And so this is where our magic star comes in. And we will use this magic star more in a moment, but it's about to become very important. So the first thing we're going to do is when we want to tell the compiler that a particular variable is to be treated as a pointer, as an address, we're going to prefix the name of the variable with the star. So it comes after the type. So for example, int x, instead of if we want to treat it as a pointer, it's going to be int star x. Now, Nupur, sorry, Jessie, I've got your name now. Okay, Nupur. So I just said that we're going to include the old type before as well as that little star at the end of it. Why might I do that? Why might I say int star instead of just star x?
Like to make a difference?
Yeah, that's a good first point. What kind of difference do I want to communicate? So let's break it down first. So let's break it down step by step. So the first thing I do is I've told you it's a star data type, which means that Madeline here is going to look in, she pulls out the number and says, oh, this is an address. And then in the next step, she comes over here and pulls out something else. Thank you, Jessie. You can come and pull it out. You put the 7 back, we're done with that variable. Pulls out the number 9. And now how do you interpret that? Nupur, what should we do to understand how to represent this? Is this a number? Is it a character? Is it another address?
It is a number.
It's a number, but we need to tell the compiler how we should actually interpret it. Because let's imagine now we have mailbox number 9 standing over there. Maybe what Madeline's going to do is she opens the first one, sees 7, goes to 7. Then she sees a 9, and then she goes over to 9. So we actually need to tell the computer what type of thing we're going to. And so that's why we do int star x, because that tells us, for example, that, thank you, Madeline, let's put it back. That's going to tell us, Finn, you're looking awfully tired. It's okay, we'll get you back soon. Having both the type and the pointer designation tells us what kind of thing it's going to. So for example, let's imagine we had 65 in here. We might want to make that variable over there at address 8 a char star, because then what we do is we go from this mailbox over here to this one. We see the value 65 inside, and 65 is a capital A. And so by telling the compiler that it's a char star, it means when we print it out, we're going to see the letter A instead of just the number 65. We need one more tool. Let's say we have our beautiful variable over here at 8, and we want to know as the user whether Madeline should actually just read out the number 7 that's inside, or whether she should do this whole sophisticated thing where she went to the other mailbox and read it out and figured out what it was. And so this is where we're going to use the dereference dance. Now this is my own invention. If you Google dereference dance, the only thing you might get is me. But again, you use the star, you do a little twirl, and then this star again is going to indicate to us that when we're accessing a variable, that what we want to do is we want to not only look inside the mailbox, but we want to look inside the mailbox, go to the next mailbox over, and read out that value. So now I'm going to hand you the star, and Nupur is going to hand you the microphone, and you're going to tell everyone that you're about to do the dereference dance. This is your moment. Get your tap shoes on.
So I go to this.
Yep, so say I'm about to do the dereference dance. Wonderful, okay. And now do the little twirl. There we go. And now perform the magic for us.
So going to mailbox 8,
Yep,
I see the value 7.
yep. We put that number back.
And then I go to the mailbox
Yep. Now we go to mailbox number 7. That's the second half of the dance.
and get that value at 9.
And now we've gotten out the value 9, and that is the full dereference dance. So let's repeat those steps one more time. I promise you this may look crazy, but when you're stuck trying to remember how pointers work, remembering the two-step dance will help. Okay, so let's do it one more time. Wait, you're missing something. Okay, so we've got the dance, great.
Then I go to mailbox 8,
Step 1, open the mailbox, pull out the variable.
goes to address 7,
Yep.
and then they get value 9.
And then gets value 9. Fantastic. We've learned the dereference dance. Can we have a big round of applause for our 5 volunteers today? Thank you very much. We can put our mailboxes back and resume our seats. And our son can get back his birthright. So let's run through this back on our slides just for a little clarity in case that demo was not doing it for you. So let's look at this setup of memory. So here I have addresses from starting at 20 in hexadecimal all the way to 78 in hexadecimal. And let's declare this variable char star A over here, and a char star, because it's a pointer and we're working in a 32-bit memory system, so 32 bits is going to be 4 bytes. 4 bytes is 32 bits because each byte has 8 bits in it, so that's going to take up 4 of our little slots over here. So each slot is going to be 8 bits or 1 byte. So to represent an address, assuming we're on a 32-bit system, 32 bits, that is 4 bytes, and each byte is 1 box and 8 bits. So you can turn that, Hani is giving me a look. You've said way too many numbers there in a short span of time. I'll try that one more time. We're on a 32-bit memory system. To represent 32 bits, we need 4 bytes. Each byte has 8 bits. So 4 by 8 is 32. There we go. There are our 4 bytes. So we've got enough room to store 1 address, assuming that each address is made up of 32 bits. Now, you'll remember that when we discussed this a little bit earlier, I said that modern computers use 64. but that just gets too hard to fit on one screen. So we're going to stick with a 32-bit computer for today. So we have our 4 bytes here, and let's read them top to bottom, 00000020. So this is just the number 0x20, but it's a char star. So at the address 0x60, we have this value 20, and if we're treating it as a pointer, now let's do the dereference dance. So I'm going to do the dereference dance with my star. So star A, which is our pointer over here, let's go up to the very top. So we're going to the address 20, and what's at address 20? It's 0x68. The basic idea is we're going to set aside 4 bytes for our address, and then we're going to dereference it so that we can actually get the value stored at that address and manipulate it. Yes. Because the computer knows that we're operating with character pointers, a character pointer, if you add 1 to it, doesn't go to the next bit. Instead of going to the next address bitwise, it's actually going to jump a whole byte, because the smallest unit that our computer can operate on is a byte, and we've already told it we're dealing with characters. So if you want to jump to the next character address, instead of going like 1 bit along, which doesn't make any sense, we're going to jump 1 byte along. So actually, A plus 1 is going to take us to this next box over here, which is 0x69 and the letter E. Our graphic in this case is going to show a pointer that actually points to another pointer. So if we remember when Madeline was at the front and I asked her, okay, so you've picked up the number 7, and now you've gone to number 7, and now you've picked up the number 9. Does that mean when you pick up the number 9, you should go to mailbox 9? That's essentially what I'm showing in this demo here, is that you can have a pointer that points to a pointer. And you can have a pointer that points to a pointer that points to a pointer, and as many stars as you like. And for each extra level of indirection meaning this instance where you go along 1 more time and do the dereference dance, we're going to add an additional star.
Why do we need to do all this? Can we just write what we want the code to say instead of jumping to all these memory points?
So the reason we need to do this is exactly what Linda showed us yesterday. Yes. Oh, not yesterday, sorry, last week, with the swapping, where we had this problem with the swapping, where we had memory that was inside a function that couldn't impact the memory inside the main function. And so if you're starting to get clever, you might think about it. If we can somehow tell the subfunction the address of the things inside the main function, then the subroutine can go and modify the things inside the main function. And that's really where we're getting at here. That's where we're going. So instead of copying the values in, we're going to copy addresses into the subroutine and then use those addresses to impact stuff back at the original location. Given an addressing system, there are multiple things you can do. And in C, most of these are going to be controlled by this star sign. The star sign, remember, is this special instruction to do the 2-step dereference dance, where we go to the location specified by the variable, we open up what's inside, and then we go to that location and then read it out again. But we are missing this third option. How do we just read the label on the outside of the box? If I have a variable, how do I know its address? Well, this is going to introduce for us 1 more operator, and this is the ampersand operator, known as the address of operator. So use this operator if you want to know the address of a variable that you've already created. Now, this is going to be easy to mess up. You will sometime probably get confused between, should I use the star or should I use the ampersand? Remember, the ampersand is for reading the label on the outside. What is the address? And the star is going to be used to do this kind of complicated dance, as well as letting the compiler know that something is actually a pointer type. So officially, the star operator is not known as the dereference dance. It's just known as the dereference operator. Unfortunately, my emails to the C standardization committee about changing the name have gone unheard. Dereferencing is just like visiting the mailbox. Just knowing the address of a location is not enough to know what's inside. You actually have to go to that location and open it up. And then again, using the ampersand operator is like checking the address on top of the mailbox. So that was Finn and what was your name again? Next to Cassie, who I can't even see anymore? Miles. So that was what Finn and Miles were doing. If you want to get the values that Finn and Miles had, those numbers that were the addresses of the mailbox, then you use this ampersand operator. Okay, so now let's actually check out how this works in a number of demos. Let's see how we can check the different values inside the C programming language and as well start to play around with it ourselves. And this is the first one of today. And again, this demo is from the book and was originally authored by Alistair Moffat, our illustrious book author. So I am on screen. Great. So what I'm doing is I'm just creating some variables to set this up. And now what I want to do, let's just print the addresses of them. That's a good way to begin. Now you'll see I'm going to start using a new format specifier, this %p. %p is the format specifier for a pointer. And I'm just telling it that I want to save this many digits for printing out that pointer so that all the addresses are the same no matter how many zeros they have out the front. Hopefully some of you have now on Ed gone to check out how to set these format specifiers. Yes, was it Jack or James? Jack.
Each time you run a program, can like the pointers change?
Yes, they will in fact change every time. And in some ways it's actually a security measure. Because if you have a high security program and every time you put the same super secret information at the same address, it might start to get easier for someone to guess where that is and try and access it if they can find other security holes. So, and let's do that. And now this time I'm actually going to remember to write the variables' names in. So let's do W, X, Y, and Z. I'm just calling it the -C is just to remind myself that this is the version that I've written in class and not the pre-prepared version. So no need to worry about that. Let's give it a run. There we go. Let's see what our output is. So the first thing we can see is that our static variable, our static integer, is at some place very different to the other ones, which all have like a similar format. You can see the static variable is at this address that is pretty low, and our other variables are at an address that's much higher. So the numbers are much, much bigger if we were to convert them to decimal. So this is probably telling us something about where in this big picture the different variables are being stored. So the static variable is stored at something low, and the stack variables, x, y, and z, are being stored somewhere high. So the static variables are going to be stored in this data segment here. Now, who knows why it's necessary for us to store our static variables in a place that's far separate from the stack? Asan, you've got the microphone. Why are we storing our static variables somewhere different? You've already answered once today. Adam will pass on you today as well. Need someone else, someone new. Okay, bright yellow shirt. Was it Michael? Yeah. Wait a minute for the microphone to come. So I'll repeat the question so you can remember what we're up to in class. So I've just seen that when I make a static variable, and remember a static variable is a variable that survives even when a function dies, it's stored in a different place to my three other variables, x, y, and z. My variables x, y, and z we know are normal variables, so they're stored on the stack. And I've just said that a static variable is going to be stored separately over there in the data segment. why might we want to store the static variable in a different place to the stack variables?
That means the different values they need to like input in different places like that.
So it's actually where the computer is storing them. So when you put them in, the computer is going to store them in a different location. Right? And the static variable, what did I say happens to normal variables when a function ends? What happens to them?
They will like deal with them and put them in the right way, like that.
When the function ends, remember, those variables are destroyed. And so if we stored our static variable over there in the stack where everything's getting destroyed, then that means when the function ends, would probably destroy the static variable as well. And our whole goal here was to avoid that variable being destroyed. We wanted static variables to survive even when the rest of the function is no longer being run. And so that's why we have the static variables located in this data segment over here. It's like a protected area that's immune from all the comings and goings of the different functions. Okay, so let's look at, thank you very much, Michael. Let's give it back to Asan. The next thing we have going on here is we can see our variables x, y, and z are being stored as we expect in the stack. And we can see these values are actually going from f1c to f18 and then to f14. So I've declared them x, y, z, and we can see they are being created in order over there. So we're going 1c minus a 32, minus an integer takes us to 1c, and minus the size of an integer again takes us to 14. That's going 4 bytes every time. Good? Okay. So that is our very first demo, and that only shows us the power of the ampersand operator. But now we want to get a little more sophisticated. So what I really, really want to get us to is what Linda did yesterday, just with a twist. Now don't worry, I'm not going to pick on you for the moment, but you're going to stay in our memories as like the problem we were having with the swapping. So let's write a new function that does our swap, only this time we're going to do it in a way such that when we do the swap is preserved inside the main function. So let's go to our swap2 program. I'm going to create a new file, and I will call this. Actually, if I'd thought about it for a more second, I would have called this Linda swap. But for now, we'll call it swap2. OK, so I'm going to create a void function, because all I want this function to do is to swap things. I don't want it to return anything. I just want it to swap its inputs. And this time, instead of giving it an integer x and y, I'm going to give it 2 pointers to integers. And essentially, I'm going to do pretty much the same thing we did yesterday. So in order to swap something, we're going to need a third variable. Let's call that an auxiliary variable, because it's not one of the 2 main ones. It's something separate. And let's call that temp. But what I want to do is I want to pour out the water from one of the variables into my temporary one. And the way I do that now is I'm actually going to have to use the star of dereferencing. The reason is because now x is just a location in memory. And what I actually want to do, right now, x is an address. It's storing an address. And what we actually want to do is we want to go to the place that x is talking about and take that value out. So I'm going to use my star of dereferencing and fill whatever the outcome of that is and put it into temp. So now I have a copy of whatever x is pointing to backed up. Next, what I want to do is I want to change what is at that address. So I'm going to say, figure out wherever x is pointing. Wherever x is pointing, throw out whatever's in there before, and now figure out where y is pointing, take whatever is in that box, and put it in this box. So we could imagine if we have our 2 variables, our 2 locations pointing to x and y, and we have 2 other variables over here that are pointing to them. So I could say, go to whatever's at x, and throw it out. Now I have a second pointer y, and y is pointing to that mailbox over there. So I'm going to go over here. take this value and make x have the same thing inside it. So it's not actually moving it, but I don't have another number 9. So for our instances, just imagine this is a copy of it. And I'm going to put that inside here. So that's what that line of code over there does. Right? And now I need my other line because I want it swapped. I don't want the value from x before thrown out. So I'm going to go to the temp mailbox. Although temp is not a pointer, so I can actually just use the value directly. And I'm going to say go to wherever y is pointing to. So y is pointing to this mailbox over here. And put whatever is in temp into this box. So that's the number 9. I'll come to you in a minute. And now all we need is a main function to test if this worked. And I'm going to do this quickly. So I will do x 5 int y equals 7 to swap. And let's just make our formatting slightly more consistent. And let's do my return 0. And I will describe the main function in a second, but first let's give it a test. Yes, where is my error, Toby? Missed a semicolon, there we go. And now we can, I need some /n's in here just to make it a little clearer. Let's run it one more time. Now we can see where initially x had 5, y had 7. Now x has 7, y equals 5. And this is inside the main function, so I've actually, from the subroutine, managed to swap them around back in the main. Now let's go through our main function just quickly, and then we'll get to your question. So the first thing we're doing, we're just setting up our variables as normal. Note that these are not pointers. They're just normal variables. They exist somewhere in memory. But what we wanted to do to create pointers out of them, we could use the ampersand operator. And the ampersand operator figures out where in memory those things are. Because ultimately, in our swap function, what we wanted to know was where are these variables x and y that we're passing in, so that if we've got their addresses, and their addresses are copied into swap, once we know their addresses, we can manipulate those addresses to swap things. And so in our main function, they're not pointers because we just want to store ordinary variables. But if we want our subroutines to know where those variables are located, that's when we're using the ampersand. The ampersand doesn't convert the variables into pointers. It just figures out what their addresses are so that we can then use those addresses in another part of the program. Yes, you had a question. And Asan, do you want to hand him the... And remind me your name again? Jerry.
In the swap function, star x and star y are pointers.
Yes.
And if you use pointers as star x, it's not referring to the value of pointer itself, but to the location it goes to.
Yes.
And can you change the pointer itself?
Yeah, can you directly change the pointer? So let's try that as an experiment. So let's go back to our pointer 1 demo. Let's do int pointer. And to make it a pointer, I'm going to put the star out the front. And I'm going to say this pointer should point to x. This is actually going to cannibalize my next demo, but that's fine. And I'm going to print x. But let's also, we know it's an integer pointer, so we can also print whatever x points to. And so to figure out what x points to, we can use star x. Actually, that should be pointer, and that should be pointer. And we know x is just a normal integer. But let's also be a little clever, and let's print the address of x and see what we get from all of these. And that should be address of x. Now let's point a new line there. Position is wrong, pointer. Star pointer, oh, address first, and then there we go. Okay, so we can see I've created, the first thing I'm doing, the first thing I'm printing is pointer. And pointer I've set to be the address of x. And then over here I'm printing out the address of x, and I can see that's exactly what it's done. So I've set pointer to the address of x, and the address of x is this value. What value is stored at x? Well, now this is actually indicating a programming bug. This is actually what x's value is, but you'll notice I've forgotten something. I've forgotten to actually initialize x to some value. So let's make that the value 40 and recompile it. Now we can see both of those are 40. So that was a bug in my program before. Now, this is a little confusing because the star operator over here is doing something different from this two-step dereference dance. What it's doing is it's declaring that my variable pointer is of type integer pointer, or pointer to an integer. That's not the same as when I write a star pointer here, which actually instructs the computer to do this multi-stage process. So another way of writing it that might be a little less confusing is to break this up into two separate lines. So on the first line, it's now very obvious that the type that I'm creating is an int star, a pointer to an integer. And in the second line, I can see what am I filling into that variable? What am I filling into the pointer? Into the pointer, I am filling the value of the address of x. Jerry, does that help? Yeah. Great. OK. So that is our next demo. Now we've got a few more that are going to give us a bit more of a feel for some of the different segments and how they work together. So these ones are going to be pre-made, and these will all be available for download after class for you to have a look at. So the first one is going to be the very simplest program that I could really possibly write. It's a main function, it does nothing, it returns 0. So now we're going to use a new command that exists on Linux systems and on Mac as well, because Mac is very closely related to Linux, and this is the size command. And this will just tell us how big are the different segments inside a program. How many bytes do we have to allocate for each of these different segments? So let's compile layout1.c. I'm going to use size-m. That's just an option to give it the right kind of output that I want. And now I can see the size of each of the segments. And I'm going to show you just very briefly what that computer code looks like. So let me, there we go, there's my terminal. So if I actually want to see what the compiler has done, it has converted my one-line C instruction into these bytes over here in this column here. And you can see as well that my command that I just ran tells us what what machine instructions that's actually equivalent to. This is called assembly language. You don't have to worry about learning it now. But if you want to get a sense of what the computer is actually doing, it's converting your C code into these numbers. And these numbers are equivalent to these instructions over here. And how many bytes are there altogether? 4,096, of which 15 are actually our main function over here. So if we were to count these, we would get to 15, and that's the lowercase text over there. Now let's look at a slightly more complicated program. And we don't actually want to run these programs, they're just to show you how much space each of the different elements of them are going to take up. So this is layout 2. Let's compile it. Layout 2 is also not actually going to do anything that we care about whatsoever. There are no real instructions in there, but we can run our size command to see. So now, if we look, we actually have the same number of bytes in the main function, almost. So let's do it for layout 1. Yep, we have the same number of instructions. Why? Well, because this instruction isn't really getting the computer to do anything. That's because all we've done is this is an instruction to the computer to set aside some memory for this particular variable. But where was this? If we look at if we look at the data segment, which remember is where we are going to store our static variables, if we look at the new entry for the data segment, now we can see that 4 bytes are taken up there in a subpart of the data segment called the BSS, which we don't really care about these sub ones, but we can see that we've taken up 4 bytes now for our static variable, our static integer I. So we can see the program is growing in size. The actual number of bytes stored on our hard drive is growing as we add variables. Now let's try out layout 3. Now I've actually changed my static variable to store some data in the store some data from the point at which I compile it. Now let's compile this one. And we can see that I am now storing that in a segment called the data segment non-caps. And the reason that I've actually changed it is because this time my variable is initialized. And so what the program's actually doing is it's saying, you know what, I'm going to save a whole chunk of the zeros that I'm just going to set up beforehand for things that are going to be 0 at the beginning, because that's really common. And so I can just set it all, this giant area to 0, and anything that needs to be 0 that's a static variable or a global variable can go there. But anything that's initialized should actually be somewhere separate, because that'll take a little more work to manipulate. But I've created a global variable in this one as well, and so that can be stored back with the zeros because it's uninitialized. And I have one more where I have an initialized global variable and an initialized static variable. So now I have 2 of these variables that actually need to have special space set aside for them at the beginning. So let's do that. And now I can see the data segment now has 8 bytes in it. 4 bytes for that global variable called global, and 4 bytes for our static integer I. So now you get a sense of where different variables are located and why their addresses might look different when we print them out. However, we've given you now this very powerful tool that allows you to pick anywhere in this giant span of addresses that go all the way from 000 to FFFFF, but most of these regions are not variables that you've created. It's either blank space in the middle, or it's a variable for another part of the program, which means once you start playing with pointers, you're much more likely to start introducing bugs into your program when you've actually set those variables incorrectly. So they're a lot of fun. They're a little mind-boggling, as we've already seen, and they can also be a bit dangerous, but hopefully throughout the semester you'll get a little more familiar with them, you'll get a little bit more comfortable and actually see how they allow us to do very powerful things. So now we will take a 5-minute break and come back at 3 p.m. I'll see you all in a few minutes. Okay, here we are, back at the stack, which is where all of our regular functions variables are going to be stored. So in C, as we've talked about, we're passed by value. So we're essentially copying the values of variables into new functions. So if we instead pass an address, that address is still going to get copied. We're still having a copy of that address made in the subfunction. But at the end of the day, if it's the address that's copied, we still know how to get back to the original. Because let's say our address is 9 Main Street, and I make a copy of that. And in my subfunction, I now have 9 Main Street. Well, by knowing 9 Main Street as the address, I can always go back to that original location, to house number 9, and change whatever is at house number 9. So by copying the address, I still can go to the original location, even though I'm inside a different part of the program. So now, if you know where a variable is in memory, and the operating system has given you permission, then you can go ahead and change it. But if the operating system hasn't given you permission, what do you get? Segfault. Now, we can set our pointers to null, even though we've said that computers will not allow us to use address 0. So if you try to dereference a null pointer, what's probably going to happen? Segfault. So this is all a trap. The star symbol is used in a number of different ways, as some of you have pointed out, and this has the potential to be very, very confusing when you're actually starting to learn how to use them. So there are 3 different ways it can be used. Firstly, the star symbol can just be used for multiplication. It will be used to indicate a variable as a pointer when you first create that variable, or when you create a new function, you might say that it takes in a pointer as input. And then the third way is the actual command to do the dereference dance. And so by keeping track of which of these are you actually intending to do, and when should you actually be using the ampersand operator instead to get the address of something you already have, that'll help you actually progress and start to use the pointers. So now we understand why scanf uses the ampersand operator. Essentially what we wanted to do is we wanted to change the variable that we've given it such that that change is visible back in the original calling function. Yes, Adam.
Yeah,
Hassan, do you want to hand him the microphone quickly?
Does that mean that if you didn't use the AND operator, scanf would interpret the argument as though it's an address when
Yes.
it's actually a value?
Yes,
Yeah.
that's right.
Right, thank you.
Toby.
What will happen if the input of user is looks like an address? What will happen?
So I'll ask the rest of the class that. What happens if we give scanf an address that's not a real address, but that's just somewhere random on the computer that we don't have permission for? That's your answer.
Oh, sure.
If you've given it, if the user has typed in something that's an address and it's actually a legitimate address, then it'll work. But yes, Jerry.
Since scanf is taking address, so can you use a pointer instead?
You can use a pointer, but the way what scanf expects in those variables is an address. So you have to be very careful about that.
If you put a pointer variable there, which
Yes.
holds an address in it's possible.
Yep, then you wouldn't have to use the ampersand symbol.
Yeah.
And for those of you who don't know what an ampersand is, it's the and sign. Okay, so we are now done with chapters 1 to 6. So you can all give yourself a cookie. Unfortunately, I don't have any cookies for us this semester, though. So this takes us to finally what many of you have been wondering: where are collections of objects? How do I do a list in C? How do I do an array in C? How do I have multiple copies of the same thing? So an array in C is going to be one of our new types, and the last major type that we're going to learn about for now. An array is just going to be a collection of objects that are all of the same type. And the reason they all have to be of the same type is because the way that C does this is it just uses the memory directly and says, okay, you want 8 integers? Well, each integer is 4 bytes, so I'm going to do 8 by 4 chunks of memory, and then you can use pointers, if you like, to go along from the start of that. You jump another 4 along, you jump another 4 along, you jump another 4 along, and all the array syntax is eventually going to be is just a fancy way of writing about pointers in the C programming language. So of course, like in any other language, we can fill up our array with different values. And we're going to do this because in almost all instances, most of the data that programmers want to interact with comes in more than just 1s and 2s and 3s and 4s. So you don't want to have to write a new variable name for each different object that you want to store. So let's say we read in 100 values from the user, and we want to store them, manipulate them, analyze them. You don't want to have to create 100 variables and then say, well, if variable 1 is already full, then use variable 2. If variable 2 is already full, use variable 3. Treating our computer's memory as just one array where we can store different values is going to be a much better way to handle this. So an array is a data type in C. This means we can use it as a type in all the ways we've used type before. But an array is also a data structure. So we learned about suffix arrays very, very early on in semester, talking about why abstraction is useful. And this is a more conceptual thing. So an array is a data structure in the sense that we can think about it conceptually and not just in the specific example of how a C program runs. So when we're trying to come up with solutions to problems, we might want to use our array as our efficient method of trying to store that data and manipulate it. Unfortunately, it's also a bit of a boring data structure, which means it doesn't have any special properties that we can take advantage of, so it's really kind of the baseline that we're going to be working with. But that's probably the wrong way of talking about it. Boring is not the word I would use. I would say useful. The array is probably the most used data type out of all the data types we're going to use for important programs. And at the end of the day, as I just said, an array in C is really just a pointer to a larger chunk of memory with a slightly different syntax. And another way of saying this is an array is a pointer with syntactic sugar. And syntactic sugar is just a fancy way that programmers say, well, we're going to hide some of the annoying syntax that you have to write and make it a little easier for you. So we have a few ways of creating arrays in C. We have a few ways of creating arrays. That's kind of fun. So the first thing we could do is we could just allocate the variable on the stack. We could say, I want room for 6 characters. Let's call this char A. And I want room for 6 of them, and that's the syntax over there. Or we could create it and at the same time already fill it up. And this is a special syntax that you can only use when you're actually creating it. You can't set arrays like this after they're created. This is only when you're initially creating them can you use this syntax down the bottom there. But it is a useful syntax. So I want to fill an array of characters with the word hello, followed by a null byte to mark the end of my set of characters. And over here, I'm doing that in, I'd have to do a second step and each individually set the letters. And this second version over there allows me to do it all at once. What I could also then do is I could create a pointer to the start of an array. And notice here that I didn't have to use the ampersand operator. And I'm going to make a quick change here because I had a char array on the previous slide. So let's also do a char array here. And I didn't have to use the ampersand operator. Why? Does anyone have an idea why I don't have to use the ampersand operator? And let's, Asan, 2 rows behind you on the edge. Yeah, you over there. Yeah.
I think that because we already store it as an array, so we don't need that operator anymore to tell that it is like an address.
Yeah, so arrays at the end of the day are just kind of like pointers in disguise. And so the reason why we don't need an ampersand operator to figure out where the start of the array is and set that to our pointer is because an array already really is kind of a pointer. It's a pointer with syntactic sugar, and so we don't need that special ampersand to tell us what the address is. The array's name is actually that address in the first instance. What was your name again? Ali, thank you very much. So as I just said, A is just a disguised pointer pointing to the start of the memory set aside for the array. So the other way we could write that is that AI is syntactic sugar for star A plus I. So getting the ith element of the array can be done in both ways, but obviously this way is a bit nicer and communicates to the world better what we want to do. So with that, let's finish off for today, and then tomorrow we'll get into actually using arrays and figuring out what they might be useful for, and we'll have our last exciting demos before I head off for 2 weeks. Thank you very much, everyone, and I will see you tomorrow.